Hello, this is a short video about Lab Activity 6, which is on collisions. I thought I would start off with a little theory, and then we can take a look at the lab and go from there. So the collisions activity actually has two parts. The first part is something called perfectly inelastic collision. So perfectly inelastic. Now this is just physics talk for sticks together. Perfectly inelastic. So again, it just means sticks together. So whenever we have collisions, we can use the concept of conservation of momentum to solve these problems. So regardless of the type of collision, whether it's perfectly inelastic, perfectly elastic, just a general kind of collision, whatever kind of collision you have, the momentum of the system before the collision, so momentum before the collision, so initial momentum is equal to the final momentum of the system. So final just means after the collision, initial means before the collision. Now the vector symbol here above initial momentum and final momentum, just as a reminder to you that you have to consider the x direction independent from the y direction. Also, in terms of the x direction, if, say, you're going to the right, that's the positive direction. Going to the left is the negative direction. So the vector symbol here is just a reminder, to you to take that into consideration. So perfectly inelastic means sticks together. The initial momentum of the system is equal to the final momentum of the system. Now, in general, for any type of collision, there's no such thing as conservation of kinetic energy. And you'll see for the perfectly inelastic collision that the initial kinetic energy is actually going to be greater than the final kinetic energy. Well, how could that be? I thought energy was conserved. Well, the total amount of energy is conserved. So the initial kinetic energy, some of it might become kinetic energy after the collision, but in terms of a collision, especially true with this perfectly inelastic kind, we generate thermal energy. So the total energy before and the total energy after is the same, but the total kinetic energy before is going to be greater than the final kinetic energy. Again, how can that be? Well, it's because we've generated thermal energy. If it were two cars crashing, you would see that the metal would deform, it would actually heat up, things like that. So we're going to test this idea out in the actual lab. Let's take a look at what this might actually look like in the actual experiment. Okay, so we'll have an initial situation. That again just means before the collision. And then we'll have a final situation. That means after the collision. So there's a couple of different masses, mass left and mass right. Okay, and they interact in several different ways. Sometimes mass left is always going to be moving in the positive direction initially. Mass right could either be moving left, right, maybe even stationary. And after the collision, again, remember this is the sticks together situation. We have mass left and mass right, and now they are stuck together. So the initial momentum is going to be equal to the final momentum again. So we can say momentum left initial plus momentum right initial. That's the initial momentum of the system. Now afterwards, I'm just going to call this like momentum final or something like that. Again, they're stuck together in that situation. Let me put a little bit more detail with this. So this would be mass left, velocity left initial plus mass right, velocity right initial. This is the initial momentum of the system. Now the final momentum of the system is mass left plus mass right, and then they have a common final speed. What I know is the initial momentum is equal to the final momentum, so these have to be equal to each other. That's what we're going to test out in the lab. We're going to see if this is actually true. In theory, this is true. Experimentally, we'll have to see how good our measurements will actually be. One thing to keep in mind, though, if you're moving to the right, that's the positive direction. If you're moving to the left, that's the negative direction. So you'll have to make sure that you take that into consideration when you put these values in. Okay, now in terms of the kinetic energy, there is no such thing as conservation of kinetic energy in general. We'll see there's a kind of collision called perfectly elastic, where the initial and the final kinetic energy are equal to each other, but that's just a special case. Okay, so let's take a look at this situation in terms of kinetic energy then. We're going to test out this idea. Again, it's not going to be true. Remember what kinetic energy is just in general. Okay, so let me clear up this page a little bit here. So kinetic energy is 1/2 mv squared. So the initial kinetic energy would be over here on this side. That's before the collision, and here's the final kinetic energy. Now the initial kinetic energy is going to be 1/2 mass left, velocity left initial squared, plus 1/2 mass right, velocity right initial squared. That's the total before the collision. Afterwards, we have 1/2 the total mass, so mass left plus mass right, and then their common final speed squared. And we'll check this out and see if it's true. It's not going to be true, but we're verifying this fact. Okay, so part of the experiment asks also how much momentum was lost, how much kinetic energy was lost. So let's take a look at how to calculate that. Okay, so we're going to look at the percent of momentum loss. So percent momentum lost. So the way to do this is we're just figuring out what fraction we have left, really. So we're going to do the final momentum minus the initial momentum, absolute value of that, divided by the initial momentum. Okay, so this will give you the fraction that's actually lost, and then multiply it by 100. That'll put it into a percentage. Okay, and then part of the lab also is to get the percent of kinetic energy lost. So percent kinetic energy lost, it's a similar formula. This would be the final kinetic energy, again that's of the system, minus the initial kinetic energy, absolute value of that, divided by the initial kinetic energy, and then the whole thing times 100. Okay, very good. Let's actually look and see what the lab looks like. Okay, so I've logged into Pivot Interactives. We're going to be doing air track collisions PNW. So let me take a look at this. So the first part is perfectly inelastic collisions. You know what that means by now. So the video shows gliders on low friction air track colliding and sticking together. There are many videos to choose from, many different masses and velocities. Try out a few to get a feel for the experiment. So the way to change this is to actually just click on collision type, a whole bunch of different ones here, left faster, right stationary, same direction, same speed, different mass combinations. So mass left and mass right. So this means left 100, right 200. That's in grams, so be careful. Okay, let's just play one and you can see what it looks like. Okay, so let me rewind it. What you hear are the designers of the experiment talking, and you can see it's actually in slow motion. And you can hear it is because of the way that their voices sound. So these are same direction. They're both moving to the right. In other words, they're both moving in the positive direction, so they have a positive velocity. And they each have a mass of 200 grams. And they're going to stick together via clay. So let's just see it again. Okay, and then they, as you can see, stuck together. So we're going to be able to measure their speeds. And the way to do this, let me back it up a little bit, play it to a part where I can stop. Okay, so it's on an air track. We're assuming that there's no friction, but of course there always is a little bit of friction. Here's the tools we have. Here's one measuring device. It's in centimeters. Be careful with that. Here's another one, and here's a stopwatch that you could reset to 0 whenever you want to. So to get the speed of this, I can measure the movement of this flag, so the flag on top here. And you can see this is about 2.5 centimeters long. So 2.5 centimeters, turn that into meters, of course, so divide that by 100, so you get 0.025 meters. We can figure out how fast this is traveling by measuring the time it takes the flag to move. And you can do this however you want to. I'm going to actually set it up like this. I'm putting this measuring device over here. I'm going to reset the clock to 0, and I'm going to see how long it takes the flag to move from this edge, which is at 0 centimeters, over to this edge. And the nice thing about this video is you can do something like this. Just advance it like this. So I had reset the clock to 0. Let me back it up a little bit with the fine control over here. So I've traveled 0.025 meters in a time of 0.3250 seconds. So you can calculate the speed that way. Let's take a look at this table down here. Oh, first there's some questions that you answer. What is perfectly inelastic, etc. So if you watch the video, which I know you have because literally you're watching it right now, you should be able to answer those questions no problem. And here's 8 different situations. Left faster, right stationary, same direction, same speed, and this combination of masses. Left faster, right stationary, same direction, same speed with this combination of masses. Okay, so this is all populated for you. Velocity left initial. So that would be the leftmost mass. That we haven't seen that yet in the picture. I mean, it will if we advance the video a little bit farther. Velocity right initial. So the one that you see up here is the right one, right? So again, the way I just described it, 0.025 meters in 0.3250 seconds, you can write that number down. Actually, let me calculate this one for us. Maybe I'll go through one row for us. 0.025 meters in 0.3250 seconds. That is 0.00769 meters per second. Okay, let me put that in the data table. So again, the one I have is same direction, 200 grams, 200 grams. So same direction, 200 grams, 200 grams. Okay, let's see. Same direction, 200 grams, 200 grams. This is the right mass, so I can then put that number here. Let's see what it was again. 0.0769. Okay. 0.0769. Let me verify that just to make sure. You don't want to make a random error here. 0.0769. All right, that looks good. So that's the right initial velocity. Let's play the video a little bit farther and see what we can come up with the left initial velocity. Okay, so I'm just pulling this direction. Okay. Now you want to make sure that the person's hand is all the way off this cart, and it looks like it is. So let me measure the speed of this one. So I'm putting the measuring device here on the edge. Same kind of flag, 2.5 centimeters long. Let me reset the clock because I just want the time for the flag to travel 2.5 centimeters. Reset the clock. And then I can do the same thing here. Advance the other edge here. And let me back it up with the fine controls over here. Okay, so you can see there's a little bit of experimental uncertainty there, right? Let me back up the video a little bit farther, maybe pick up a different point where I get a cleaner looking picture. Okay, try to move the ruler. See, it's a little difficult. Not too bad. Okay, I think that looks pretty good. Reset the clock to 0. Advance this to this edge. And then again down here I can use the fine controls. Whoops. I almost get better control by doing it by hand, it looks like to me. Maybe not. Okay. Okay, so I'm going to say this is 0.1167 seconds. But I've changed things around, so I'm not completely confident that I reset the clock before I did that measurement. So let me back it up again. Reset the clock to 0. Start over, put this on the edge. That looks pretty good. 0 seconds. All right, let me see how long it takes to go the whole length here. And I'm going to the edge. Okay, so I have to do a little bit of estimating, but I think I'm just going to go with 0.025 meters in 0.1167 seconds. And let's see what that speed would be. So that's the leftmost glider. All right, let me actually calculate this. So 0.025 divided by 0.1167. Whoops. 0.1167. Okay, so 0.214. 0.2142, maybe I'll use 0.2142. Okay, let's go down to the data table. 0.2142. And that's the left one. Definitely it's faster, right? That's the one that we were looking at, same direction. So for them to collide, the left one has to be going faster than the right one. So 0.2142. 0.2142. Okay, so we've got the initial speed of both of them. One more measurement to make here. We want to get the speed after they've stuck together. Now we're assuming after they stuck together they have the same speed, which they should. Okay, I'm advancing this slowly. They hit with the clay right about there, and then they start moving off. Now I want to get it as soon as I can after they collide. If I try to make the measurement way down over here, that means that they maybe slow down due to friction a little bit. Probably not a lot, but a little bit. So let me make sure that they've stuck together, and then they're starting to move off. Okay, so that's probably pretty good. I can do the same thing. I only have to measure one of these flags, though, because they're going with the same speed. Okay, so I'm setting this measuring device here. Let me reset this to 0, and then see how long it takes to travel that length. This is them stuck together. All right, that's pretty good right there, I'd say. Okay, so 0.1833. So 0.1833 seconds for the system, both of them stuck together, to travel 0.025 meters. So let's calculate that. Okay, so what I had again was, clear this first, 0.025 meters, and this happened in 0.18, whoops, 181, there we go, 833 seconds. So, okay, so their combined speed, 0.1364 if I round it up, 0.1364. Okay, so let me go down to the data table here. 0.1364, that's their combined speed. So if you go over here, velocity final, that's them stuck together. 0.1364. Okay, and you can notice this is in meters per second, masses are in kilograms. Okay, so we want to get the total momentum. This is the part we're going to have to do the calculations. Now you could just do it by hand from how I showed you before for each of these. I mean, you could go through literally and do mass left, velocity left initial, plus mass right, velocity right initial, add those together. But we could let pivot do the work for us. So change column formula. I've clicked on the 3 dots, change column formula. So the initial momentum would be the left mass times velocity left initial plus mass right, velocity right initial. Okay, so that is what the initial momentum of the system is. Now, both of these were traveling to the right, so both velocities were positive. Now, if one of them is traveling to the left, you have to, on your own, insert the negative sign. We just measured distance divided by time. Really, we measured the speed to think about that as a velocity, you have to assign right positive, left negative. And actually, I think I need to fix this. See if I can clear it. Now let me cancel and start over because I didn't put the multiplication sign in there. So change column formula. Mass left times velocity left initial plus mass right times velocity right initial. Okay, so this is the initial momentum of the system. Okay, now let's get the total final momentum. Remember, that's when they're actually stuck together. Change column formula. So this is the total mass. Let me do it like this. Parenthesis, mass left plus mass right, close parenthesis, and then times their final common speed, so final velocity. Okay, mass left plus mass right times their common final speed. Submit. Oh, okay, so we did lose a little bit, but not much really. So this was the initial momentum, 0.05822. Here's the final momentum, 0.05456. You'll also have to calculate the percent momentum lost. I showed you how to do that in the first part. I recommend just doing it with the formula here. You know, again, go up here, change column formula, and you can pick anything you want here, and it'll do it really easily for you. So when you populate these other cells, so say you go back and you do the other trials, once you put the numbers in here, it should give you the final momentum and the initial momentum. Okay, and you can see it's changed colors here. So go through and do all these different arrangements. Just be careful again if something's moving to the left. It's up to you to put the negative sign in here for the velocities. Okay, so have some fun with that. And one other thing to say, let me show you another collision type. Same direction. Let me pick, let's see. Let me pick maybe left faster, and I think this is the one I'm looking for. So left is going to be moving faster, but the left has a smaller mass now. This would be mass left, mass right. I think this is the one I want to show you. Let me just play and have them collide. Bam. Okay, so let me show you that one again. This is a interesting case. So first of all, mass right, the speed of mass right is negative because it's heading in the left direction. So again, the same thing, figure out the distance, the time, but then you have to put the negative sign. Mass left over here is moving to the right, so its velocity is positive. But once they collide, they stop. So the final velocity of the system is 0 when they stop. So in the data table for this one, final velocity would be 0. So the final momentum of the system is 0. Well, it turns out, well, I don't want to give too much away. You'll have to work it out and see how that actually works out. Okay, so that's the first part. Kind of a lot of work here, but once you get going, it goes pretty fast with measuring these different things. Okay, good. So let's look at the second part, and again from what you do here after you do the data table. There's no graphs for this one, just the data table. From your data, would you say momentum is conserved? Use your data to support. So probably it's not going to be 0% loss, but you know, is it pretty close? What are the reasons for that? Use complete sentences, you know, and justify your claims. From your data, would you say kinetic energy is conserved? And then again, use your data to support your claim. So more than just 2 words, you know, say whether it is and then support your claims. And then the second part, perfectly elastic, one doesn't have as many trials. There's only, if you come down here, mass into stationary mass, mass at equal speed. So there's only 2 different ones. These both actually have the same speed. So this doesn't take as long to get the data. These don't stick together. Perfectly elastic means that's a special case. The initial and final momentum are going to be equal regardless of the type of collision. But perfectly elastic is a special case where the initial kinetic energy is equal to the final kinetic energy. Okay? So let's see, according to the data table, we have mass into stationary mass. So let me change the scenario here. Mass into stationary mass. That's the first one in the data table. I might as well do that one first. So these collide via magnets, so they don't hit each other. This is a nice gentle collision. So this is the same thing. This is mass right. The other one coming out is mass left. That part's already been populated in the data table for you. So this one's not moving initially, so its initial speed is 0. So down here, velocity right initial for this one is 0 because it's not moving. Now get ready, this is almost like magic. So there's magnets here. They interacted via a magnet. So one came in. Back it up here. So velocity of the left one final is 0 because this one stopped. That's why I say it's almost like magic. It just interacted. The left one is initially moving, the right one's not. Afterwards, the right one's moving, but the left one's not. So if something's not moving, its velocity is 0. So when you put that in the data table, that's how you represent that. The other scenario, they're both actually moving. So make sure you pick the correct point in the data table to put these. Oh, let me hit play here. Okay, so as you can see, perfect. Again, same idea. If you're moving to the right, what you measure is the speed. If you're moving to the right in the data table, that's a positive velocity. If you're moving to the left, you have to assign the negative sign in terms of the velocity. Okay, so same thing, go through, populate the velocities here, and then now if you notice the difference between this data table and the other data table, the other table only had one final speed. Well, it's because they were stuck together and they have the same final speed. So here there's left velocity final and velocity right final. So there's an additional column here. The rest of it's the same though. Just be careful though, because the final momentum of the perfectly elastic situation, they're not stuck together anymore. So the final momentum, is slightly different. I mean, it's the same idea. The final momentum would be mass left, velocity left final, plus mass right, velocity right final. And again, be careful with the signs. In the sticks together part, the final momentum was different. It was a different formula because the masses were stuck together. Here they're not stuck together, which means they don't have the same common final speed. So you'll have to take that into consideration when you figure out the total final momentum. Total momentum initial, total momentum final, percent loss, kinetic energy, that sort of thing. Okay. Hope you have some fun with it. You're not making any graphs this time, just data tables. And once you get going, it actually goes pretty quickly. So hopefully after you've done this lab, you'll learn the difference between what really perfectly inelastic and perfectly elastic types of collisions mean. If you have any questions, contact your lab instructor.